Okay, it's my pleasure to introduce our third tutorial speaker, Sylvy Anscombe from University of Paris. She will tell us about Ax-Kochen Ershov results.
Thanks for coming and thanks for inviting me, the organisers. Yes, so let's get stuck in. But maybe I can say, as this is a tutorial talk, don't hesitate to interrupt me if I assume something that you don't know, or if I go too quickly, too slowly, or too quiet, if I'm too loud. Any of that, please don't hesitate to interrupt me. So basically, I want to talk about Ax-Kochen Ershov, which is a collection of results beginning in the 1960s about the model theory of valued fields. But with very solid algebraic applications. It's kind of the core body of results that underline a lot of contemporary research in both applied model theory and the more abstract parts of model theory that focus on using valued fields as sort of a guiding family of examples. But this isn't. I don't see this as being largely about model theory. A lot of this is about the structure and algebra of valued fields. Subject to various sort of hypotheses that play the role of completeness, or bigness, or enoughness. And the main hypothesis that I'll play around with is henselianity. So hypotheses like completeness, henselianity. Maybe in some first baby examples, I'll say, I'll look at the case when things are algebraically closed. And then later on in the week, I'll get to sort of tameness, Kuhlmann hypotheses, etc. Other kinds of settings. But basically, structure and algebra of valued fields with various of these kinds of hypotheses. Our kind of key words are, I want to get towards understanding the want, and what's our goal. I want to understand what are theories in first order logic of important friends like fields of power series, maybe p-adic numbers, even R. What do we know about these things? And maybe we care about positive characteristics. We could look at more general Hahn series, etc. So One theme is just, let's try to understand what these theories are. This is the problem of identifying complete theories. You know, can I give a list of axioms? You know, for some such theories? That's the sort of general question I'm interested in. But I also want to know, what are the definable sets? In these structures, for example. These structures, and I can write them. I want to know, are there some algorithms that help us answer first order questions? That's a bit like asking this, what are the complete theories question, but with an eye to knowing whether you can answer that question algorithmically. So are there algorithms to decide such theories? Much like, you know, these questions that Kuhlmann was just discussing. Okay, so that's a kind of little overview of the kind of questions I want to ask. And I already showed you some of our key friends. Let me just get stuck in to giving a few kind of reference materials that I've now managed to get chalk goo on my. All right, so some references. Lots of books. I know that I'm very much aiming this, by the way, at non-model theorists, I should say. So model theorists, please take a coffee. At least for the first couple of lectures. You know, so I will introduce somewhat carefully, some of the basic kind of model theory ideas and tools. And if some of that's still feeling uncomfortable for you, then I can recommend the books by Hodges. There's several model theory books by Hodges, or Marker, David Marker. I could give lots and lots of recommendations, but Tent, Ziegler, various other people. This is the sort of model theory reading list. I could give you the reading. I could point towards Engler and Prestel, the book on valued fields, and Fried Jarden's bit of a very useful tome. All things in this ballpark. There are also lecture notes by Lau van den Dries. Franziska Jahnke also has some lecture notes. These are sort of more clearly referenced in the online version of this that I'll also make available. And there are various others. Okay. So, let's start with some ingredients from logic and model theory. So I know that not everyone's a big friend of logic. So let me just start with the basics. So languages our best way of introducing languages, I think, is through the example of the language of rings. L ring, which has as a signature something like this. Well, we have two binary symbols, plus and times, one unary symbol, subtraction, and two constants, or zero symbols, if you like, 0 and 1, which in any actual ring, we will always just mean the obvious thing. So in an actual ring, the symbol will always be plus, and so on and so on and so on. There's no great magic to it. You've seen the notion of a structure satisfying a formula earlier, and I'm just saying that since we're only talking about rings and fields and valued fields, things are what they seem. And then formulas in this signature are built up as you expect. Using, in this case, I'm focusing on using polynomial equalities and inequalities together with conjunctions, that's and, disjunctions, negations, implications, by implication, a good sprinkling of parentheses, and importantly some quantifiers which range over single variables. So this is the characteristic property of first order logic, that you allow yourself to quantify over single variables, but not over sets, functions, and so on. Okay, so this is the basic framework of the first order logic of rings. And of course, we have several major tools, such as the compactness theorem, which says the following. Maybe I could sprinkle some names here, like Gödel, Maltsev, and Henken. Things like this were known to a lot of people around that time. The first order theory, which means set of sentences in the first order language, is satisfiable as a model if and only if it is finitely satisfiable. I remember Satis was my report card from my maths teacher when I was 10. Just that one word. So it's worth noting that the compactness theorem is a delicate set theoretic thing if you care about arbitrary languages, but we mostly don't. We mostly care about straightforward languages with finite or countable signatures. And for such languages, it's just a fact of ZF. So there's no magic here. It's just a fact, at least when you're in the countable languages world, if you like ZF. Okay.
Did you say what's finitely satisfiable?
Sorry.
Did you say what's finitely
Oh,
satisfiable?
yes, I didn't say that, thanks. I.e., every finite t prime is satisfiable. Thanks. Okay, so theorem, the Lowenheim-Skolem theorem. I'm going to, at the same time as telling you what this theorem is, I want to remind you perhaps about elementary extensions. This is a sort of, slightly, it's a version of Lowenheim-Skolem. So let M be, let's just say an infinite L structure. Remember, when L is just the language of rings, that's not necessarily just a ring, but you won't go far wrong if you think now Sylvy's taking a ring. In fact, we're at liberty to interpret symbols wildly and with no particular meaning or with a different meaning altogether, but we're not going to do that today. We're not doing that kind of logic. So take a ring, an infinite L structure, two statements now. let kappa be some, you know, some huge cardinal. There exists another L structure, N, with big cardinality, and which is a logically nice extension of N. We write that like this, and now I'll tell you what it means. This is an elementary extension. Which means, now I'll give you the definition in this box, for every L formula phi, some variables, x bar, some x bar long tuple a bar from M. This is just a bunch of ring elements in the basic standard setting that we're playing with, mostly. This is just some kind of first order statement about rings, but really it's about some n unknown elements. That's what I'm saying. And then I'm going to plug in those a's, and the definition is that for any such m believes phi of a exactly when n does. So the slogan here is, as far as elements of M are concerned, M believes exactly the same statements as N does. That's about as nice a notion as you could imagine of what a logically nice extension of a structure should be. In case you wonder, that's supposed to be a slightly curly sort of inequality symbol. And that's one of the strongest notions of kind of extension that one has in elementary extension. So this theorem is telling you, without loss, if we're only interested in the theory of an object, or bear in mind, I want to say quickly, since I'm allowed to look at zero-array tuples here, this is in particular saying M and N have the same theory. These sentences that don't refer to any variables freely, that don't have any variables left to vary. They're sort of all bounded by quantifiers. Even when I first started teaching in France, they teach that to first years, which surprised me. I'd never heard of that till I was studying logic later on. You know, what's the difference between a sentence and a formula? So, anyway, what this is saying is that when you're concerned only about theories, you may as well take as large structures as you like. You can blow up to some huge structure, N, if you like, of whatever cardinality you like. There's a lot more to be said about that kind of technique, but this is the first hint of it. Okay, so that's the upward part of the Kuhlmann theorem. Now's a good chance to ask something. So there's a downward part, right? The downward part, I can express. I could be a bit more precise than what I'm going to tell you, but for our purposes today, it's good enough if I tell you that the downward Henselian theorem is essentially when you're dealing with a countable language, you might as well go down to a countable structure. I'll say that a bit more symbolically now. I've done my, and I've paid my dues. Yeah.
So is it the same to be an elementary extension and to be elementary equivalent?
No, these are very different things. Perhaps I'll say something like that now. So I'll tell you, I'll clarify that just after I finish this downward part. So the downward part says, remember I took M to be an infinite L structure. So there also exists N0, a different one, which is countable. Sorry, that's my mistake. I mean, suppose now that the language, the set of formulas in the language is countable. Again, I'll never play around with uncountable entities. Then there exists a smaller structure, N, my N's and my LF0s look very similar, which is indeed countable and lives inside M as one of these elementary, but now I've flipped the arrow, elementary substructures. Same notion, but flipped direction. Okay? So that says the kind of opposite thing. If we're only interested in theories, and we're in a countable language, we might as well assume we've got a small model. That's often another useful kind of trick. And the moral of all of this is that we've got a lot of flexibility when looking at first-order questions about what cardinality of object we play with. That's the moral. The first-order questions, we have flexibility about the cardinality of our structures. Now, Vincent's question was, is elementary substructure or extension, is that really the same as saying have the same theory? And the answer is no. So that's maybe a bit of a caution if you're new to this. Caution, dangerous bend ahead. Caution, not all first order equivalent structures M and N, this is written M triple line N, are in the relation, M like this, or even the other way around. And that's not just for the dumb reason that maybe one is somehow technically not a substructure of the other. They can well be that one is a substructure of the other, and yet that relation is not the logically nice kind. There are very many boring examples of that, some less boring exercise. Okay. So I have another very serious ingredient to give you now, which is Wash's theorem. Now I heard Jen say just a minute ago, did Jen? I don't like ultra products. Someone said that.
I definitely did that.
I wasn't you. Okay, someone said, I don't like ultra products. Well, Wash's theorem is what tells you how to understand ultra products. So, first I should tell you what an ultra product is, but I'll do that mid-theorem. So, let AI be any indexed families of structures in some language. So this could be a family of rings, family of fields, a family of strange structures that don't happen to be rings but are in the language of rings. Or we could be playing with groups or graphs or whatever it is. But if you want to think of rings, think of rings. And normally, I is going to be something like n. Maybe it could be the set of primes, but it's some sort of indexing set. And again, I'm never going to play with this notion beyond the countable. So you might as well think of it as n. Okay, now let's take now U, an ultra filter. That's the sort of slightly complicated part on I. That means, so it's a maximal filter. Enough. Maximal filter, i.e., where a filter is a subset of the power set of I with, let me say, filter. I'll just say what it means. The empty set is not in there. We're not allowed to use the empty set if X is in this collection and Y is some superset of X. Of course, that should still be contained in the index set I. Then Y ought to be there, so it's closed upwards, and it's closed under intersections. So X and Y in U implies X intersect Y. And I probably want it to be non-empty, so I might as well just say, for example, I is in there because, if something's in there and it's closed upwards, then obviously I is in there. So fine. So that's a filter, right? And a maximal one is an ultrafilter. What on earth is that? Well, it's some sort of notion of a big subset of I. That's the intuition. An ultrafilter is a collection of sets, just subsets of some fixed universe, which are sort of giving us a notion of bigness. I am a big subset of I if I'm in this ultrafilter U. And in general, there'll be lots and lots of choices for ultrafilters on some even countable set I. I'll come back to that in a second. And we use this notion of bigness to take a limit. So we take some ultrafilter on I, and now we can form the ultra product which is the direct product, like that, just as sets. And then I quotient by the ultrafilter, meaning I quotient by, because what are the elements in here? They're tuples indexed by I, where each ith coordinate lives in AI. You quotient by the relation, well, we are two tuples, infinite tuples, that are equal on a big set of coordinates. Okay. So just for clarity, a little I, the sequence, is in relation with AI prime, means that the set of i's, set of indices, where they actually agree, is a big set according to you. That's all it is. Okay? Now, the first notion of a filter you ever saw was the co-finite thing. We're co-finitely equal. We're almost everywhere equal somehow. Right? Or maybe it was eventually equal, or maybe it was something to do with limits of real functions as they go to infinity. There are lots of notions of filters and ultrafilters out there that you see in normal maths. Anyway, so we can take this direct product, we quotient by this thing, and we can even then give it a structure. Now, I'm not going to tell you the full gory details because that's a bit boring, but basically the addition, if these were rings, the addition and multiplication would of course carry to this direct product of rings. If they were fields, it wouldn't be a field anymore, in general. And when you quotient, all of that structure passes down. This is in fact coming from the quotient by an ideal. So that is now a ring. So this really inherits an L structure. It inherits a natural L structure. In fact, whatever your language is, the same process works, even if it's a language with relation symbols and such like. Okay, so there is a structure here. It somehow amalgamates all the structures on the AIs. Now I've announced this as a theorem, but it's looking suspiciously like a definition. So let's say then, what's going to be true now? The theory is somehow determined by the ultrafilter, right? So then the theory of this ultra product should be somehow a limit according to U of the theories of each factor. So this is the following. The theory of this, meaning which phi's are believed by this structure, well, that's easy to write down now. It's those phi's such that the set of indices where phi is true is a big set. And that's true for every L sentence, every assertion, formula without any free variables. So that's the thing. Walsh's theorem just tells you the theory is what it probably should be. Now, why am I telling you this as well as the compactness theorem? Yes, you can go to the compactness theorem via Walsh's theorem if you like. You can notice that this is a way of building bigger structures from smaller ones. Okay, that depends a little bit on some counting. But also it's a way of amalgamating different structures with different theories. So it's got its own use, it's got its own value. Also something very interesting. Suppose I told you, here's a field. Suppose I tell you, you can play some game with this field using the compactness theorem, where, in some elementary extension, something nice happens, like, some map has a section. That's sort of fine, but what else do we know about that field? The new extension. What else? What does the compactness theorem tell us? Not a lot directly. But constructions like this, combined with that way of thinking, tell you that you can usually, of course I haven't given you a specific setting, but usually lift additional structure from your starting structure to some supposed bigger elementary extension. That's a way of lifting more than the original kind of just raw compactness approach might have told you. Okay. I just wanted to give you that intuition. Now do some more wiping. Any more questions? All right. Too slow, too fast, too much logic, too little logic? Actually, seriously, I would like to know what is especially the PhD students in the room, can you give me a steer on your comfort level with I've got one thumb up. Can I have thumbs plural? They can go downwards, they're all going up. Okay, so that means I'm going a bit too slow, probably. Is that right?
No.
Right?
You're going right, just don't go faster.
Not faster, not slower. Okay, speed is a total order, that tells me I'm just right. Okay. Alright, so, now, I hope you can excuse me these logical introductions, because from a model theory point of view, these are the basics. Maybe if you're not a model theorist, maybe it looks a bit scary, but really that's it. In terms of big ingredients, that's it. We're not doing anything much more advanced than that, purely from a model theoretic tools point of view. Okay, I will mention the word type. some point soon, but I'm not going to use any sort of more sort of hardcore combinatorial things. And the moral, as I said, is that we're allowed to make structures bigger while keeping their theories the same. That's really the main moral of all of this. Okay. So now let's talk about some model theory of fields. Because valued fields are, after all, I believe, are fields. And you know, there are a couple of underlying ingredients that we can't avoid thinking about. So, Tarski is the pioneer here. Tarski investigated the L-ring theories of he investigated many things, but let's say C, R, and FP bar, by which I mean algebraic closure, and I'm going to tell you what they are. I might be being a little bit anachronistic. I don't know if Tarski really cared about FP bar, did he? No idea. Okay. So, firstly, it's worth noting we could let F somehow be a set of L-ring sentences consisting of the usual axioms of fields. Consisting of field axioms. Right? Just the usual ones that you remember when you first saw fields as a first year undergrad, for all x, for all y, for all z, x, y, z is x, y, z, and so on. These things are basic examples of first order statements. So we've got a theory of fields. At least that's an axiomatization, and then any sentence phi that's true in every field will then, by a version of the compactness theorem, be a purely formal consequence of these axioms. We can also let ACF be F union phi n, preferably n a natural number, where phi n is a first order sentence in the language of rings expressing every one variable polynomial which is non-constant has a root. Every one variable polynomial of degree at most n, that's what I wanted to say. Every one variable polynomial of degree at most n, which is non-constant, just to avoid some sort of trivialities. I don't want to end up demanding that 0 equals 1 or something like that. Has a root, right? ACF, this together with this, is a good candidate for some kind of theory of algebraically closed fields. So it's immediately clear that C, by which I mean the obvious L-ring structure C, models this theory. Right? There's no magic here. This is just a statement that C is a field, so it believes the field axioms, and it believes that it's algebraically closed. It's a true statement. Yes?
So wait, is this ACF only requires one root?
I'm only asking that every suitable polynomial has a root.
Okay.
And that's enough to then get that every polynomial has as many roots as it should do.
Oh, okay.
I'm not talking about roots being distinct and so on, just that they just that they exist. It's also pretty clear that FP bar believes this theory. But these are boring mathematical statements. These are not, there's nothing fancy logic-y going on here, right? It's just a logic-y way of writing that C and the algebraic closure of FP are actually algebraically closed. Right? That's all. There's no special verification of this statement moved. That's all. It's also, I mean, I could write Q bar or whatever, right? Really, that's exactly the common, well, it's certainly contained within the common theory of all algebraically closed fields. Is it actually somehow the common theory of all algebraically closed fields? By which I mean, you know, if some statement were true in all algebraically closed fields, would it necessarily be a formal consequence of this, whatever that should mean? Well, the answer is yes, and that's Gödel's completeness theorem, which I haven't formally stated, but you can believe that somehow this means what it should mean. Axioms mean semantically and formally. Everything can be deduced somehow. Everything that's true in every model is true somehow purely formally from the axioms. All right, and you know, obviously R is not a model, right? X squared plus 1 doesn't have a root. That is a one variable polynomial of degree at most 2, which is non-constant, but it doesn't have a root. So R is not a model, and of course, nor's a lot of other fields we could name. Right? So that's kind of just how theories work. Little exercise for you is just to write down some actual sentence in the language of rings, you know, with the brackets correctly and everything that says this. That's a nice little exercise. Note, thinking about Bjorn's talk, note that both F and ACF are listable. Well, hang on, let's be a bit careful. What am I saying? They're not literally listable because they're just sets of formulas, sets of sentences. So we need to be a bit more careful than that. But if we numbered every symbol in this language, remember there's only finitely many symbols flying around, really. If we numbered them with some, maybe letter, actually, A, B, C, D, E, then every formula is really a word, and a very basic computer program could tell us which words, which finite words are meaningful statements. And then we can ask which of those meaningful statements are axioms in this set. Well, that's a finite set, isn't it? That's the axioms of fields for all x, for all y, for all z. So that's an easy thing for a computer program to tell us whether this, whether a given string of symbols is an axiom. So it's even stronger than listable. It's actually decidable, computable. No, yeah, I don't want to write decidable. I'll say computable sets with suitable codings. This ABC business, that's just some way of coding things up, so I'm not going to explicitly get into that. ACF also, although there's now an infinite number, it's pretty clear that if you do the exercise and write down some first order way of formalizing this, you're going to do it. You could do it differently for each n. This is a really interesting thought exercise. You could do it differently and wildly for each n. Right? You could just add on some sort of truism, some sort of tautology which varied somehow chaotically in undecidability with each n. You could do that, but actually you couldn't. We couldn't do that. There's no process to do that, more or less. There's no human, there's no deterministic process to do that. So if you follow your nose and do this in one of the many sensible ways, which us as humans would do, then you will end up producing a computable list of axioms. Right? And then it's true that the set of consequences of these theories, F and ACF, formal consequences, are then listable. Right, that's the same sort of idea that Bjorn was just telling us about. If you want to check a Diophantine set, if you want to write down a program that just takes your Diophantine equation and you want to list all the, I forgot exactly how you phrased it now, but check which x's, for which x's there are some y's and z's and a's and b's that satisfy a given equation. Well, you can just start listing all possibilities. You just start checking all witnesses up to 10, all witnesses up to 11, all witnesses up to 12. And of course that in principle takes infinitely long if you want to be sure that some x isn't in there. That's why listable and computable are different. But ultimately it is listable. Okay. So that's an interesting observation.
Maybe I'll comment for the students. When we think about programs, they actually operate on words, on strings of symbols, and not on integers. So you don't have to code. The notion of listable can be explained without needing to have to code these sentences or as natural numbers.
Yeah, we can absolutely do that too. Okay, let's move on. So Tarski, I haven't told you what Tarski did yet. I've just outlined what these theories are. Well, Tarski proved, I need one more ingredient. So now, for each p, a prime number, can you think of a statement that is true about f p alg that is not true about c? Yes, you can. It says 1 plus 1 plus 1 plus 1, p times is 0. Right? So for each p, we could write down this sentence just as a sort of, I'm just meaning like this. 1 plus 1 plus 1 equals 0. That's a suitably bracketed, which I'm omitting for readability, with suitable parentheses, and I mean this is p times now. This is a bona fide sentence in this language of rings, right? I'm not cheating. Modulo what I said about brackets. Let's note that p is not here a variable in the sentence. That's a really important principle in logic, just to be a little bit careful about that, right? The sentence chi2 is just 1 plus 1 equals 0. The sentence chi5 is 1 plus 1 plus 1 plus 1 plus 1 equals 0. There's not one sentence with a variable p. Then write ACF p for ACF together with chi p, and that's for p a prime, and I'm going to write ACF 0 for ACF together with negation. That's the not symbol, chi p, and that's for all primes. Okay? So this is now at least called the theory of algebraically closed fields of characteristic p. This will be called the theory of algebraically closed fields of characteristic 0. And Tarski's theorem, ACF p and ACF 0, many things listed here, are complete. Let me just highlight what that means. That means, i.e., if K and L both model ACF P, and that's for, I really want to highlight, that means for the same P, which I temporarily allow to be 0, then K and L are elementarily equivalent, have the same theory. I wrote that down somewhere a few boards ago. This is the symbol for have the same sentences, have the same theory. Believe the same sentences, have the same theory. Right? So the consequence of that is that nothing is true about one K that isn't also true about all other algebraically closed fields of the same characteristic. And this leads us to maybe I can borrow a bit of board here. And this leads us to a little kind of observation, which is that if you let U be a so-called non-principal ultrafilter on the primes, non-principal means that it's not coming from just saying, for example, the principal filter at 2 is the one that says, I'm a big set if and only if I contain the number 2. That's really taking an ultra product with respect to that kind of filter just takes the second, or just takes the structure corresponding to the index 2. That's a sort of boring ultra product. Right? It just sort of collapses to being one of the structures you've listed. It's like you've taken a direct product and then just immediately projected it onto one coordinate, that's all. So that's a boring sort. Well, take a non-boring sort, like this, then the corresponding ultra product of the FP alges, or bars, and bar, pound, squiggle, quotient by that ultrafilter, that is elementarily equivalent to C. That's a very curious thing. Let's just trace through why that's true. Well, if I'm true for C, if I'm a sentence that's true about C, then in fact I'm in the deductive closure of this theory. I follow from these axioms. Well, one way of looking at that is now ask yourself, does this structure, ask yourself what is the characteristic of this structure? Well, it can't be 2, because only P equals 2 coordinate structure believes that, all the others believe not that. So the not is the bigger set. And so on. So this has no finite characteristics, so it's infinite characteristics, so this already believes that all these axioms over here. And I just said that the sentence believed of C is exactly those that. So that's a sort of consequence of it. Okay. A little exercise for you. Show ACF 0 is not finitely axiomatizable. There is no finite set of axioms that has the same models, has the same class of models. Can I get a time check? When did we actually start? Was it 45?
Go to 45.
Yeah.
Okay, marvelous. Thank you. Okay. And another exercise for you is just look into theory of real closed fields. Just find out what some axioms are about real closed fields.
So it shows ACF 0 and or for ACF P.
Say again, sorry.
So the exercise is for show ACF 0 or for show ACF P. I mean 0 is always not finite. So.
Well, I mean, I agree with you that ACF 0 is not finite axiomatizable. Maybe I misunderstood your question, actually, I'm sorry.
Okay, so the exercise is only for 0 or for IVP. I think for ACF P is also not finite satisfied.
Oh, yeah, that's also true. Yeah, that's also true. You're absolutely welcome to show that ACF P is not.
Yeah, because calculated 0, you don't need algebraic code.
Yeah, that's also true.
Sorry, can you repeat what's the question for? Sorry, what's the first exercise?
Show that. So the first thing was an example. I was just giving you a kind of the thing at the top, x. But then exercises show that For example, ACF0 is not finite axiomatizable. Meaning there's no finite set of sentences, axioms, which are equivalent, meaning has the same model. Really what this is asking you to do is to sort of take an arbitrary finite set. Okay, well, maybe as a first step, it's asking you to take a finite subset of the axioms that I've given you and show that there's a structure that models that finite set, but which is not actually modeling everything. So either it should fail to be algebraically closed, or it should fail to be a characteristic zero, or it should perhaps even fail in a more trivial way. And then you have to show that if there was some finite axioms, then there would be some finite collection of axioms within a given axiomatization. Sort of two-step argument. It's not trivial. Do both steps, I find.
Is it easy to see that those two elementary equivalent structures are not isomorphic?
It might be.
They are isomorphic. In the first exercise, they are isomorphic. They are isomorphic.
Yeah.
There you go.
Same.
It was easy.
How did you build that isomorphism?
Well, you have to. I mean, it has the same. They have the same cardinality.
Yeah.
And then
Yeah,
you
but
use.
this is exactly the proof of. This is also the proof of Tarski's theorem.
And then you can use transcendent spaces. No,
Exactly.
they have the same transcendent spaces.
So the question that we're discussing is, what's the right argument here? And one can see this exactly by observing that these will be isomorphic, which is really the same argument that goes into this proof anyway. Essentially, one way of proving this, one quite direct way, is to say up to isomorphism within a sufficiently large cardinality, there's exactly one ACFP, whatever, up to isomorphism, there's exactly one. And that exactly uses this technology of transcendence bases and so on. So that's the argument that goes here, and also directly can argue for this. Okay. All right. So, moving on. I want to tell you what. I mean, this is not just this is a very important baby case, even though it has no valuation. Why is it an important baby case? Because there's what I would call the standard conclusion. Which is the following. Let B, it's going to be a collection of sentences in this language, be the Boolean combinations of these sentences chi p that's p a prime there is a computable function epsilon from the collection of all sentences in this language for B such that ACF believes every phi to be equivalent to its image epsilon phi. Now what on earth does this mean? Perhaps Doug's point is that we don't need to worry too much about the coding. There is some function given to us by a Turing machine, an algorithm, whatever, which takes an arbitrary first-order question, a statement, which may be true or false, and tells us Well, it's true in characteristic 2, it's true in characteristic 7, it's true in characteristic 65,000, whatever it is, but false everywhere else. Right? So that's our first kind of decidability theoretic conclusion, even in this baby case about algebraically closed fields. And that is because of the uniformity of all of these sort of algebraic completeness and model theoretic completeness statements. So this is another kind of compactness phenomenon. So this comes about, sort of like a proof idea. The existence of some function, epsilon, not necessarily, I mean, ignoring computability, is coming from, or is by, the separation theorem, which I'm ignoring, which I'm omitting, but it's essentially a form of compactness. Sort of more or less equivalent to compactness. Yes, there's a question.
Sorry, what was phi in this situation?
Anything in the domain, any sentence in the language of rings.
So what does it mean for ACF to model? I'm confused with that appreciation.
Yeah, okay, maybe I skipped a little step in my notation or introduction. Thank you for noticing. So, this symbol gets used in two related but different ways, right? One is about structures believing things, which just means this is true here. And the other is about, you say, a theory entails a thing.
Yeah.
And what that means, which is what I've written here, but I didn't fully tell you what that is. And that means that every model of T also believes phi.
No, I'm confused about what does it mean to model phi to the second one.
Is equivalent to?
Oh, I thought that was hook right arrow.
Okay, sorry. Yeah, okay. I love the way LaTeX has completely into our vocabulary. I thought you meant hook right arrow. I thought you meant slash hook right arrow. Okay. Happy? I mean, I haven't told you the proof because it's A, not hard, B, quite standard, and maybe not terribly illustrative, except for me to say that I always get reminded in this proof, it's not quite the same statement, but I always get reminded of the fact that a compact T2 space is T4, is normal. Something like that. You know, these arguments where you take covers, you take an open cover here, you've got a closed subset of a compact space, and you then say, well, you know, finitely many will do it, and isolating me from some given point here, and then I say, but there's now an open set here, and they all cover this, and so now I've got two lots of finite sets, two finite lots of open covers, which don't meet, you know, and that's how you get normality if you've done a little bit of basic topology. But so it's that sort of argument, but using the compactness of these spaces of sentences. Okay.
So in words, this is saying that, well, first of all, given any first order sentence in the language of fields, the set of this, I mean, it'll be true for if you look at which characteristics, it's for algebraically closed fields of which characteristics through, it's either going to be a finite set of characteristics or a cofinite set of characteristics.
Exactly.
And moreover, it's saying that given the sentence, you can actually compute that finite or cofinite set in an algorithmic way.
That's a very, very valuable point, thank you. I said Boolean, right? And that means finite Boolean combination. So the finite combination of things that say, I am of characteristic 7. Boolean includes not, so it's finite Boolean combination of characteristics. So it's, in particular, it's finite or cofinite.
So Boolean includes and, or, and not.
Yeah. So in the end, it's just a finite or cofinite set. That's what that's exactly what that's saying. So it's eliminating, computably eliminating to a finite or cofinite set of characteristics, and it's
So what does the backward arrow mean?
this thing is equivalent to. This is just a silly logical way of saying that in every algebraically closed field, this is true if and only if this is true, meaning that field has that characteristic that's described by this finite or cofinite set. Okay. I see that I'm out of time, and I'm about a third of the way through my first lecture. All right, so I'll leave you with one exercise, is to learn about the Ax-Kochen.
Can you write it on the board?
Yes. The exercise, which is exactly based on the tools that we've just been using, learn about. Just Google it. Just read the Wikipedia page once. You know, learn about the Ax-Kochen. Which guy's name I always forget. Without that E.
And there.
Yeah, exactly. Thank you. Theorem. It's not fun if I don't tell you what it is. Like, it's a very straightforward statement, which actually now you have all the tools to prove. Sorry for going over time. Thanks for your attention.